functions, if I apply the derivative operator to x squared, I get 2x. Now if I also apply the derivative operator to x squared plus 1, I also get 2x. If I apply the derivative operator to x squared plus pi, I also get 2x. The derivative of x squared is 2x. Derivative with respect to x of pi of a constant is just 0. The derivative with respect to x of 1 is just a constant, it's just 0. So once again, this is just going to be equal to 2x. In general, the derivative with respect to x of x squared plus any constant is going to be equal to 2x. The derivative of x squared with respect to x is 2x. Derivative of a constant with respect to x. A constant does not change with respect to x, so it's just equal to 0. So you take the derivative, you apply the derivative operator to any of these expressions, and you get 2x. Now let's go the other way around. Let's think about the antiderivative. Antiderivative. And one way to think about it is we're doing the opposite of the derivative operator. The derivative operator, you get an expression and you find its derivative. Now what we want to do is, given some expression, we want to find what it could be the derivative of. What it could be the derivative of. So if someone were to tell you, or give you 2x, if someone were to say 2x, let me write this. So if someone were to ask you, what is 2x the derivative of, they're essentially asking you for the antiderivative. And so you could say, well, 2x is the derivative of x squared. You could say 2x is the derivative of x squared, but you could also say 2x is the derivative of x squared plus 1. You could also say that 2x is the derivative of x squared plus pi. I think you get the general idea. So if you wanted to write it in the most general sense, you would write that 2x is the derivative of x squared plus some constant. So this is what you would consider the x. Now that's all nice, but this is kind of clumsy to have to write the sentence like this, so let's come up with some notation for the antiderivative. And the convention here is to use kind of a strange looking notation, is to use a big elongated s looking thing like that, and a dx around the function that you're trying to take the antiderivative of. So in this case, it would look something like this. This is just saying this is equal to the antiderivative of 2x. And the antiderivative of 2x, we have already seen, is x squared plus c. Now, you might be saying, why do we use this type of crazy notation? It'll become more obvious when we study the definite integral and areas under curves and taking sums of rectangles in order to approximate the area of the curve. Here, it really should just be viewed as a notation for antiderivative. And this notation right over here, this whole expression is called the indefinite integral. The indefinite integral of 2x, which is another way of just saying the antiderivative of 2x. With respect to x, of x to the n plus 1th power over n plus 1 plus some constant c. And we're going to assume here, because we want this expression to be defined, we're going to assume that n does not equal -1. If it equaled -1, we'd be dividing by 0, and we haven't defined what that means. So let's take the derivative here. So this is going to be equal to, well, the derivative of x to the n plus 1 over n plus 1, we can just use the power rule over here. So our exponent is n plus 1. We can bring it out front. So it's going to be n plus 1 times x to the, I want to use that same color. Colors are the hard part. Times x to the, instead of n plus 1, we subtract 1 from the exponent. This is just the power rule. So n plus 1 minus 1 is going to be n. And then we can't forget that we were dividing by this n plus 1. So we have divided by n plus 1. And then we have plus c, the derivative of a constant with respect to x. A constant does not change as x changes, so it is just going to be 0. So plus 0. And since n is not equal -1, we know that this is going to be defined. This is just going to be something divided by itself, which is just going to be 1. And this whole thing simplifies to x to the n. So the derivative of this thing, and this is in very general terms, is equal to x to the n. So given that, what is the antiderivative? Let me switch colors here. What is the antiderivative of x to the n? Of x to the n. And remember, this is just the kind of strange looking notation we use. It'll make more sense when we start doing definite integrals. But what is the antiderivative of x to the n? And we could say the antiderivative with respect to x if we want to. And another way of calling this is the indefinite integral. Indefinite integral. Well, we know this is saying x to the n is the derivative of what? Well, we just figured out it's the derivative of this thing, and we've written it in very general terms. We're actually encapsulating multiple constants here. We can have x to the n plus 1 over n plus 1 plus 0 plus 1 plus 2 plus pi plus a billion. So this is going to be equal to x to the n plus 1 over n plus 1 plus c. The reverse power rule. And it applies for any n as long as n does not equal negative 1. Let me make that very clear. N does not equal negative 1. Once again, this thing would be undefined if n were equal to negative 1. So let's do a couple of examples just to apply this. You could call it the reverse power rule if you want, or the anti-power rule. So let's take the antiderivative of x to the 5th power. What is the antiderivative of x to the 5th? Well, all we have to say is, well, look, the 5 is equal to the n. We just have to increment the exponent by 1. So this is going to be equal to x to the 5 plus 1 power. And then we divide by that same value. Whatever the exponent was, when you increment it by 1, we divide by that same value. Divided by 5 plus 1. And of course, we want to encapsulate all of the possible antiderivatives. So you put the c right over there. So this is going to be equal to x to the 6th over 6 plus c. And you can verify. Take the derivative of this using the power rule. You indeed get x to the 5th. Let's try another one. Let's try, now we do it in blue. Let's try the antiderivative of, well, let's make it interesting. Let's make it 5 times x to the negative 2 power dx. So how would we evaluate this? Well, one simplification you can do, and I haven't rigorously proven it to you just yet, but we know that scalars can go in and out of the derivative operator when you're multiplying by a scalar. So this is indeed equal to 5 times the antiderivative of x to the negative 2 power dx. And now we can just use, I guess we can call this anti-power rule. So this is going to be equal to 5 times x to the negative 2 power plus 1 over the negative 2 power plus 1 plus some constant right over here. And then we can rewrite this as 5 times negative 2 power plus 1 is x to the negative 1 over negative 2 plus 1 is negative 1 plus some constant. And this is equal to 5 times negative x to the negative 1 plus some constant. And then if we want, we can distribute the 5. So this is equal to negative 5 x to the negative 1. Now we could write plus 5 times some constant, but this is just an arbitrary constant. So this is still just an arbitrary constant. So maybe we could have written of this, if you wanted to show us different constants, you could say this is C1, C1, C1. You multiply 5 times C1, you get another constant. We could just call that C, which is equal to 5 times C1. But there you have it, negative 5 x to the negative 1 plus c. And once again, all of these, try to evaluate the derivative, and you will see that you get this business right over there.